Okay, welcome. Welcome all of you. Um, welcome, of course, our special guest, Peter Bruce, today, who is sitting in the UK, in Oxford, waiting to present his lecture in about 15 minutes. I'm happy to have, of course, uh, fully consistent with the Corona rules, a few guys and PIs, members of the faculty here in the lecture hall. It's a bit of a strange impression here for me, but I know that most of you are in the virtual background listening as audience. And I think it's, despite all the strange boundary conditions, really a great pleasure for all of us and for Peter Klar and me as chairman of the executive board to welcome you to the opening of the Center for Materials Research, ZFM, Zentrum für Materialforschung, formerly known as Laboratory for Materials Research. And before we will have a few words of greeting from our rector, Professor Mukherjee, and before Peter will give his lecture, let me very briefly give you a bit of background of what we celebrate today. I think some of you will know that we started about 2002, 2003, when we had really a serious lack in students in physics and chemistry departments, when we thought it's a good idea to study a joint program in material science. And from that on, and you see that with the uprising, say, strategic development, in green is study programs, in blue is the precursor to our Center for Materials Research, and yellow and red is research programs. So I think the materials research and material science history in Gießen essentially started almost 20 years ago. And I think before I continue, I think I would like to remember that at this beginning is really closely linked with a person whom I think many of us really miss, to Bruno Meyer, who had the chair in solid state physics, and in this early period was really a key driver. He was also my key partner in driving, installing the bachelor and master scheme for material science. And I remember many evenings with him, with and without wine, discussing how to shape the material science bachelor and master program. And what you see behind him on the right picture is, I think, the first generation of students who all get really excellent jobs in material science. So I think we will never forget him. And I remember very well, as chemists, we often are a bit careful and we often tend to stick to too many rules. And Bruno, I think, always said, okay, let's simply do it. Let's try it. Let's make it, and don't have too many. Don't think of too many barriers and hurdles. Now, today, in the mid of 2020, I think we have gone quite a way and we have been very successful. And to make the story short, what you see here is just a little summary of the projects, the collaborative projects and institutional projects we have started. And the key point is that from the early point on, where we had to become first a laboratory of material science, because at that time we were not, I would say, strong enough to form a center, and the center of the university has to fulfill certain rules. We developed, and the last 5 years, the state ministry of Hesse supported us on that way. Finally, we had in winter an evaluation by external reviewers. The evaluation was really very pleasing, and as the outcome, the university decided to really inaugurate us as a full center, interdisciplinary center of the university. And that's what we celebrate in principle today. We are now really probably one of I think maybe the biggest center, interdisciplinary research center of the university. And effectively that will start from the beginning of next year, but of course, will already operate right now. I think on that way, I think there have been many successes, and I think I would only like to mention a recent success, very much driven by Peter Klar and by Sangam Chatterjee. And what you see here, again, already consistent with Corona rules. At the left, you see our state minister for research, for science and culture, Angela Dorn, and she is handing over a document that states, or let's say, is the funding agreement on two EFRA labs, so two labs funded by European money, one on high performance materials and one for physics under harsh conditions, where also some chemistry groups are being involved, which form a new way of cooperation, formalized cooperation with industry. And I think that's something we are really quite proud of, that our physics colleagues organized that. Now, in a certain sense, that we meet today in this format is also somehow a disappointment that we couldn't run our normal materials day. You know, we have very close ties to Marburg University and to our University of Applied Sciences here in Gießen as long-term partnerships. So since really many years, we have every year in summer a joint materials day. We meet either in Marburg or in Gießen, and you see some pictures here from our partners. And I think this is another element, I think, of our strategic development, that we have these very close ties with our neighboring universities in the field of material science. And if we count, I think, the groups in material science in these three universities, I think we can count up to 70 full groups with professorial PIs in the field of material science, which I think forms one of the biggest entities, or let's say research clusters on material science within Germany. Now, our center today, I think it provides broad support to all its members. We join forces for collaborative projects. I think in Gießen alone, we have more than 50 senior experts, faculty members, and senior scientists in various fields. We have more than 200 members, at least, I think, 150 or 160 PhD students enrolled in the material science programs. We have a very successful program to recruit junior research groups. One just left us, Wolfgang Zeyer, I think, who is known probably also to Peter Bruce for his work in solid electrolytes, went to Münster, but we also already have new members like Felix Richter, who just also got a big grant to build up his research group as others. So I will not go into detail, but I think the combination of research, teaching, both supporting undergraduate teaching, but also graduate teaching, cooperation with industry, running our own platforms, sharing our own expensive equipment, so that all the PhD students can, I would say, really hurdle-free or barrier-free move to any group and use the other machines, of course, under certain rules, but I think in a very nice and barrier-free way, is, I think, really one specific element characteristics of our center. Now, that brings me, of course, to the point that at the bottom, what is very important is our intense international cooperation. I'm happy that I see at least one of our students from the double degree program with Padua University in the material science field. And of course, I'm also happy that Peter from the UK, as an international colleague, gives his presentation today. Now, before I close, I would like to remember again to the starting of our laboratory, when we thought, okay, we need a logo. And at that time, well, it was quite natural. The little acronym of Laboratory for Material Science or Materials Research is the LAMA, which in Latin is the Lama Glama. And if you look up a bit, I think it's quite clear why we choose then the llama really as part of our logo. Llamas are very social, as we are. So we like to be together, to cluster. And of course, in this current situation, it's a pity that we can't have a big party, which we otherwise would have immediately after an event, as always. Llamas are extremely curious. I think this is the same for us. We need to be curious. That's an essential part in science. Without our individual curiosity, we would never be successful. And every member of us should be as curious as possible to be successful. We approach people easily. I think that's not always true for every natural scientist, but often we're a bit introverted. But I think that within the llama, things are quite easy. And it's easy to be extroverted. And what is also important is llamas can carry about 25 to 30% of their body weight for quite a distance. So llamas are also, I would say, quite strong and able to work hard. and I think this is the same with us. So I think the llama is still, I think, a good, I would say, symbol or part of a logo. And so we thought what to do. You know, this is our old logo, which looks a bit, I would say, unusual for logos. It's quite curved and looks not so technical like many logos. And the story of that is that simply a postdoc and a PhD student, when we started, I asked them, oh, can you create a logo? And they did it. And it was more like a fun that they created this a bit of McDonald's looking logo with this M and the spitting llama. Uh, Fortunately, well, let's say interestingly, we said, okay, that's great, let's take it. And they were really surprised. And so for more than 10 years, we had the spitting llama as our logo. Now, okay, as we run into a new period, Elisa Monte, who is working in the EFRA projects with Peter and Sangam, created a new logo, which is the ZFM now. And because we all love the llama and would really, would say, miss it, Elisa had the nice idea to put the llama at the right top as a kind of copyright symbol. So it's still there. It will be with us. And so in all the different styles of the new logo, and I think this is, I think, quite a nice thing. So in our new logo, even in the new design, I would say part of our history and well, our characteristics is being involved. So with that, I think I would like to really thank, of course, all those who have helped on our way to become an interdisciplinary research center of the university with, fortunately, of course, also central money supporting us so that we are able to run the center and do the good things we like to do. So, of course, we thank the state ministry for financial support on the way. We thank the university for continuous financial and administrative support, and of course, to take major, I think, major part of the funding from 21 on, all third-party funding institutions, particularly the European regional funds, all partners in industry and academia. We have a lot of partners in industry, and I know that this cooperation will hopefully further increase. Of course, the partners in Marburg, Kerstin Volz and all her colleagues, for also continued cooperation and hopefully also strengthening cooperation. I would like to thank Thomas Leichtweiss, Martin Gönrich, our two coordinators, from Martin is today assisting technically here, and I send all my best wishes to Thomas, who is for a short parental leave because he and his wife just got a child. And of course, to my co-chair Peter Klar in physics, I think our center, or I think the major part of the success of our center is that we do everything 50 by 50. So hopefully 50 by 50 chemistry and physics. And I think this trust in our mutual cooperation is always there. And I thank Peter for long years of trustful cooperation. And of course, all the PIs, postdocs, and PhD students in the center for doing all the hard work llamas should do, and all the undergraduate students that are here and form, of course, the next generation. With that, I thank you for your attention. And with a, I think, probably little technical break, we switch over to greetings from Professor Joybrato Mukherjee, president of our university, who is this week on vacation, but sends his greetings in a video, which we will start now.
Ladies and gentlemen, dear colleagues, dear guests, as President of Justus Liebig University Gießen, it is my pleasure to welcome you to this special colloquium hosted by the Center of Materials Research, the ZFM. In addition to providing a forum in which special topics in materials research are discussed, today's colloquium is also a celebration. We celebrate the continuation of the ZFM as an interdisciplinary research center of our university after its successful evaluation by experts. Congratulations! The successful evaluation of the ZFM in 2020 is the culmination of many years of dedicated and consistent work by the management and members of the ZFM and its predecessor institution, the Laboratory for Materials Science, short LAMA. When the results of the ZFM's evaluation reached the university's executive board at the beginning of 2020, I was very proud to read the exceedingly positive assessments by the experts. I would like to thank everyone involved in the ZFM for all their hard work and enthusiasm that propelled the successful development of this institution. The Center of Materials Research is truly an excellent example of an interdisciplinary joint venture. The departments of chemistry and physics act as equal partners. Each contributes their expertise and perspectives to further the ZFM's common goals in research, graduate training, and collaboration with regional and international partners. It is no coincidence that our university has been pursuing a consistent strategy of strengthening research and teaching in materials science over the last 15 years. Materials research plays a major role in Justus Liebig University's research profile and development planning. In 2018, we defined the field of materials and energy, with a focus on storage materials, as a so-called area of potential in our research strategy called the Liebig concept. This means that we plan to further strengthen and expand research in this area. The Center of Materials Research has been instrumental in growing this research area in the past and will certainly continue playing a key role in this process in the future. In addition to its commitment to excellence in research and teaching, the ZFM also makes science communication a priority. The members of the center engage with students, fellow researchers, industry partners, and interested laypeople through a variety of formats and media, ranging from discussion formats like today's colloquium to the center's Twitter account. In the winter semester 2017-18, the ZFM's managing director, Professor Janek, co-organized the president's annual lecture series on the topic Energiewende, that is, the transformation of the energy system. The ZFM also realized an impressive accompanying program for pupils and the interested public, which was very well received. These efforts to reach out beyond our own labs, departments, and specialized circles is invaluable, especially in these challenging times in which skepticism towards scientific fact has become dangerously accepted in some circles and isolationist tendencies are on the rise. Therefore, I am very glad that today's symposium, which is open to everyone interested, is taking place despite the difficulties associated with the COVID-19 pandemic and that local as well as international guests are involved. I thank the organizers, especially Managing Director Professor Janek, for hosting this event and the afternoon's keynote speaker, Professor Bruce from the University of Oxford, for contributing to this special colloquium. I wish everyone here today, whether in person or via video conference, an interesting afternoon with stimulating discussions and new insights. And of course, this is a well-deserved opportunity to celebrate the Center of Materials Research, its members and partners. I am confident that the future ahead will be bright and wish you all the best. Thank you.
And let me very briefly introduce Peter Bruce to you. We had invited him, of course, for our materials day between University of Marburg and Hessen. I know that the Marburg people also will attend today, but thought it's a good idea to invite Peter then in exchange for the event that could not take place physically to today's event. Now, Peter is a chemist, so he has his PhD in chemistry from the University of Aberdeen with Anthony West, who is well known in the field of solid-state chemistry. Later was postdoc with John Goodenough, I think, who is also well known to most of you as a Nobel laureate. And then via several steps, in particular, I would say the University of St. Andrews in Scotland, where he really, I would say, helped very much to bring the chemistry department up to one of the top places. Meanwhile, he has moved to Oxford. He is Vice President, Physical Secretary of the Royal Society. the UK Academy of Sciences. And well, I think there has a long list of other awards, services, and I think I don't want to go into that, but it's really a long list, and I'm happy to share that with you, but not now. I think what I should mention is that Peter was very successful in also helping to install the so-called Faraday institution within the Faraday within a, so say, UK government industrial strategy challenge fund. So in principle, he helped or he persuaded the government to invest a major amount of money, up to 250 million pounds, into research, into the so-called Faraday challenge. And he himself is part of the, as a PI or chief scientist of the Faraday Institution, which deals with research around energy and the future of energy and devices around energies. In particular, his interest is solid state batteries currently in that institution. But maybe as part of the talk, Peter can give a few words on that. So, Peter, I know that you have a very narrow schedule, and it's a great pleasure to have you here, I would say, with us. I think the transmission looks excellent, so the stage is yours, Peter.
Jürgen, thank you very much indeed. It's very kind of you, your kind introduction, and that also of President Mukherjee. Of course, it's a deep regret that I can't be with you all in person because of this crisis the world is facing, but hopefully we'll have a vaccine soon and we'll be able to all meet again physically, which I look forward to very much. And I want to also, of course, congratulate you on this wonderful center that is an evolution of your activities that you had before. It seems a very exciting place to do science. So with all that, let me move to my presentation and to thank you for the opportunity to talk to you today. And I hope you find what I have to say stimulating and interesting. We'll go through some slides, and I'm going to talk about the title you see in front of you. This, by the way, is not a picture of my labs anywhere. This is an aerial view of Oxford. My labs are slightly more modern than the buildings you see before you. So the title of my talk is Climbing the Energy Ladder, Lithium Battery Cathodes Invoking Oxygen Redox. Now, I'm sure I don't have to tell this very well-informed audience how significant lithium battery technology has become worldwide. And of course, there's always an appetite from those who want to use lithium batteries to have higher energy density, so electric vehicles can be driven for longer distances between recharging, etc. And so one of the big challenges that always faces us is how to increase the energy storage per unit mass and volume. And as I'll talk about in the next slide a little bit more, that challenge, of course, has many facets, and some of them are engineering, about packaging, etc. But some of them certainly are about the fundamental science. And within the fundamental science, one of the biggest challenges we face is how to increase the energy storage in the cathode, which is normally a lithium transition metal oxide. And conventionally, the charge storage is involved storing electrons on transition metal ions. And the question that we've been looking at, and many others in the field, and I want to talk about today, is whether one can extend the storage of charge of electrons in cathodes in lithium transition metal oxides for lithium batteries, whether one can extend it from the transition metal to the oxygen. And so that is the challenge that we face. And we've been very much involved as others in understanding what might underpin the science that might underpin realizing that ambition. So again, I won't go through how a lithium-ion battery works. I'm sure everyone is familiar with this, but I put this slide here really just to remind you that to increase the energy storage of a lithium-ion battery, one has to increase the storage of lithium ions and electrons, both in the negative electrode, represented here as graphite, and in the positive electrode, represented here as lithium cobalt oxide. Now, we have arguably some routes to improve the storage of lithium in the anode, moving from more silicon-rich to more silicon-rich anodes from graphite. But as I mentioned a moment ago, one of the bottlenecks or the barriers or the challenges around increasing the energy storage in a lithium-ion battery is how to increase the amount of lithium, especially the redox capacity, if you like, of the transition metal oxide cathode. So currently, and this is a rather general comment, but I think it makes the point, we are largely limited to store electrons on the transition metal and one redox couple. But to increase the energy storage, we have to increase the energy density. Sorry, to increase the energy density, we have to increase the energy storage in the cathode. So if we look at some metrics, if you like, for cathodes, what I'm going to show you here is the potential range over which some of these lithium transition metal cathodes operate and their capacity. So potential on the y-axis, capacity on the x-axis. So this is the classic lithium cobalt oxide that was pioneered by John Goodenough that Jürgen kindly mentioned. I worked with him in Oxford many years ago. And this shows you the capacity typically and the voltage range. This is represents the so-called NMC materials. And so having mixed transition metals on the transition metal sites, it's been a huge focus of research in battery cathodes over the last many years. And you can see it increases capacity at a similar voltage. Remember, energy storage depends on the voltage of the cell and the amount of charge one can store in the electrodes. So you want every electron that moves from anode to cathode to go through a large potential difference, because every time that happens, you get more energy than if it's a low potential difference. So that's why both potential and capacity are important. Now, those comments lead me to show you these two materials, which of course operate at high voltages, so you get more energy storage, although their capacities, as you can see, are somewhat limited. Now, the difficulty here is, in practice, the organic-based electrolytes that we use in these liquid-based lithium-ion cells, in any case, are limited to maybe 4.5, 4.8 volts. So these high-voltage materials would be very challenging for that and many other reasons. And then we have efforts to increase the capacity of transition metal redox by things like the lithium vanadyl phosphates, which attempt to invoke two redox reactions, two redox states. And then the topic of today, you see in the light blue curve here, which are the so-called lithium-rich compounds, which can invoke oxygen redox. And you see the benefit here is that they operate in a similar voltage range to the sort of so-called classical materials, but they offer extra capacity at high voltage, but also within the usable voltage range, so not too high to be impractical. So the message here is that these lithium-rich materials can both increase the capacity to store lithium, to store charge, and do so at a relatively high voltage. So that's the good news, and that's why there's such interest in these materials as a potential way forward in the development of high energy density lithium-ion batteries. But now we have to look, of course, at the challenges, because as the economist Milton Friedman said, there's no such thing as a free lunch, and there certainly isn't in this area either. So the compound that I'm going to talk about quite often as a nice model of these sorts of so-called oxygen redox or lithium-rich materials is the one that you see in the top left-hand side here. It's a layered transition metal oxide. Instead of having cobalt in between the square brackets, which represents the ions on the transition metal sites, you have a mixture of not only nickel, manganese, and cobalt, as one has in the mixed NMC materials, but also lithium. So this is a lithium-rich material, and this is important that you now have lithium on these transition metal sites. So here's a representation of the crystal structure. Here are the lithium layers, the alkali metal layers, and here are the transition metal layers with cobalt, manganese, nickel, and also lithium. So what you see on the right is a typical load curve, a typical voltage versus capacity or composition along the bottom here curve as one charges a cell with one of these materials as the cathode and then subsequently discharges it. And you see with the shading that the initial charging process is largely associated with transition metal redox. So one extracts lithium as one charges, and that is charge balanced by the oxidation of the transition metal ions, in this case mainly nickel, but also cobalt. And if you stop here and then come back again on discharge, you will follow pretty much the same curve. But if you enter this higher capacity region, where you see this plateau, this is when we're starting to oxidize oxide ions. And now what you notice is that on the way back, on discharge, you have a large loss of voltage. And loss of voltage means, of course, loss of useful energy. So typically 1 volt, 1 electron volt is lost on the first cycle of this material. So you come back down here, you're getting out less than you put in. So once you start moving into the oxygen redox region, the chemistry, the physics of what's happening here is quite different from a transition metal center redox process. Now, if you keep on cycling, you get the black curve. So you still get some hysteresis. In fact, this is what I would call real hysteresis, because a hysteresis loop goes round like this. We talk about hysteresis on the first cycle. It's generally a term used, and I will use it for that reason. But in a sense, it's not really hysteresis. It's irreversible voltage loss. You never get it back, as you can see here. So, of course, you could operate in this region here and accept that loss of the high voltage and therefore the higher energy that one could get from the cell. But ideally, one would like to cycle along this region here, where you can actually access the high voltage and higher energy density. So the problems you can see are writ large here. The voltage loss, the subsequent cycling at lower voltage, but also you see a change in the voltage curve, which is called voltage fade, and we have to understand this problem. And we have to understand, of course, what's going on in the second and subsequent cycles, as well as this voltage loss on the first one. But a lot of the focus in this part of the talk will be on this large voltage loss and whether we can understand its origin and whether we can stop it happening. So that's simply the point that's made here. Irreversible change in the voltage in the first cycle, of course, signals a change in structure. This irreversible change of energetics, of the energy of the reaction, tells us that something is happening irreversibly to the structure. So all of this means that if we're going to try to avoid that and get to ultimately a material where we can cycle at high voltage, we need to understand the nature of oxygen redox fundamentally. What happens when we oxidize oxide ions? We know that some oxygen is evolved, sometimes more, sometimes less. But can we understand what controls the direct loss of oxygen, of molecular oxygen from the surface? Do we create Hall states on oxide ions in the bulk of the particles in the valence band? Do we create peroxide ions? And this would be analogous to what happens in sulfides, where we know that you can oxidize an S2-, 2- charges to this dimeric disulfur 2- species. Or do we form some other species? And how does all of this trigger the voltage change, the structural change that we see? So let me just first of all show you something on the oxygen loss question, because it's interesting that when these materials were first discovered more than 20 years ago, the original explanation for this extra capacity was that we were simply losing molecular oxygen, and then after that, reduction was involved reduction of the transition metal ions and then conventional transition metal redox. And what you'll see here is that there is some oxygen loss, as I touched on earlier, but it's actually only a small part of the story. But to investigate the oxygen loss, we use this arrangement here. This is a DEMS arrangement, a mass spec arrangement, where one carries out the electrochemistry in the cell and, of course, passes argon gas into a mass spec to analyze the gases evolved. And so these are the results. Here's the charge and discharge curve again, so-called opened out this time. These are the two principal gases that we're interested in, molecular oxygen and CO2. And I should say that we're using a material here which is oxygen 18 labeled, so that we know that any of the species that we find are associated with the oxygen that has come from the lattice, from the material, and not simply from decomposition of the organic-based electrolyte at these sorts of potentials. And so if we look at, first of all, the results for molecular oxygen, one sees some molecular oxygen with O18 is evolved here. We see CO2 evolved across the plateau with, again, oxygen 18. And we now understand, and it was very nice work by Hubert Gasteiger in Munich that actually showed that what was happening here was all dioxygen loss, but it was singlet oxygen, a reactive singlet oxygen, and this attacks the organic electrolyte to produce the CO2. And then later you get direct oxygen loss. So the point about this, the take-home message from all of this, is that you get molecular oxygen lost from the surface of the particles, but it's a small proportion of the total capacity. That's the key point. There is oxygen loss, as the original researchers thought, but it is not the whole story. It's not even half the story. It's a small part of the oxygen redox story. Most of the oxygen redox is associated with a process taking place in the bulk and is not due to direct oxygen loss at the surface. So to try to understand what the nature of oxygen redox is in the bulk material, various groups around the world have been putting huge effort into this. We're just one of them, so I don't claim by any means all the credit here. Many people have made important and are making important contributions. And are using different techniques. And one of the techniques that we have found useful, and others too, is RIX, resonant inelastic X-ray scattering. So just to remind you how this works, one ejects an electron from a core state to the empty states here, and then looks at the decay of electrons from the filled states just under here back to the core level. And if one does this for the oxygen 1s, the oxygen K edge absorption, then it's oxygen K RIX spectroscopy. And the oxygen RIX is a very useful probe of the nature of the oxygen electronic states, especially mapping out the oxygen valence states, as we'll see. So here's our charge and discharge curve again for our favored material, this lithium, nickel, cobalt, manganese material, the archetypal example, I think, of a layered lithium-rich material with excess capacity. And there's our plateau related to oxidation of oxide ions again. And I'm now going to show you this RIX spectra collected at several key points along this curve. So here's the RIX spectrum collected at the beginning of the plateau. This is the end of the normal transition metal process, where we're just entering the oxygen redox process, the oxide ion oxidation. Now, I should explain these RIX maps. I'm sure many of them are familiar, but basically what we're plotting on the x-axis here is the various excitation energies used, and for each excitation energy, one is effectively collects an emission spectrum passing along the x direction, and that's what forms these maps. I mean, they look very pretty, but I'm not sure they actually tell you a huge amount. I think I'll show you an expanded region at one excitation energy, which I think is more informative. But I mean, they are useful, and they show you where there is mapping out emission, as you see. Now you see a RIX map collected at the end of oxidizing our oxide ions, end of charging here. And those with good eyesight might spot that there are some features in this region. But I'm going to make it easier for you. I'm going to expand this region up, and you should see it now here. So this black curve is the expansion of this region here. So this is the elastic peak at zero energy loss. And if you compare this with this spectrum, RIX spectrum for molecular oxygen, you'll see the same spacings. This is effectively a vibrational spectrum, and this is the vibrational spectrum of molecular oxygen. So it's a very precise fingerprint that shows you that there is molecular oxygen at the end of charge. Just for interest for those involved in this, this is a spectrum for lithium peroxide with obviously peroxide ions, and you see it doesn't match the spectrum that we observe in our cathode material. Again, if you notice here in the material before the plateau, before the oxygen plateau, there is no evidence of this vibrational spectrum, no feature here. And then if we look at the end of discharge again, we see that these features have gone. Here's the expanded region, and we're back to something that looks very similar to the pristine spectrum. So the take-home message, if you like, is that when you oxidize oxide ions, you actually form molecular oxygen that isn't molecular oxygen evolved from the surface. This is a ultra-high vacuum ex situ measurement, the RICS. It's oxygen trapped in the lattice in the material. And it's a reversible process in the sense that you can re-reduce that oxygen back to oxide ions. And indeed, I don't know if I have it here. No, I don't. But you can go around that the second cycle, and you can see oxygen formed again, and again back to oxide ions on discharge. But can we understand then how this is possible in this material? How is it possible when you charge the material, when you extract lithium and oxidize oxide ions? How is it possible to accommodate a molecular oxygen in the structure? So here's the crystal structure again. We're looking along the planes here. So here's the lithium layers and the transition metal layers, as I showed you before. And then if we have a sort of bird's eye view looking down this way, this is what we'll see. This is the plan view, if you like, of a transition metal layer. And if you remember in X-ray diffraction, there is virtually no difference in the scattering between cobalt, manganese, and nickel. So all of these will look similar. You can see that this is a very nice honeycomb structure. This is the lithium here. It's the classic honeycomb structure that one sees, or superstructure, I should say, that one sees in most of these lithium-rich compounds. And on the right, you see a powder diffraction pattern for this material. And here's the expanded region in this rectangle. And these are the superstructure peaks. And you can assign these peaks to this honeycomb superstructure. So this is just experimental evidence showing you that you have this nice hexagonal superstructure. Now, what happens when you charge a cell with this material? So let's first of all look at some scanning transmission electron microscopy of the particles on doing so. So first of all, this is a STEM image, again looking along the layers, along the 0, 1, 0 direction, before charging. And these dumbbells, the light features here, of course, are the heavy scatterers, the transition metal ions in STEM. So these dumbbell arrangements here that you see are very characteristic of what the honeycomb structure looks like when you're looking along the layers. If you contrast that with the charged material, you see that contrast of light and dark along a transition metal layer has gone. It's largely now washed out. And this is very much in accord with the transition metals disordering within the layers. You see there's not a lot of light between the layers where the light alkali metal ions would normally be. Of course, they're mostly removed in the charged state. But this shows us that we're not getting a lot of transition metals ions moving out of the layers, but they're disordering principally within the layers. And these other two pieces of evidence here are simply support that. You see this is the powder diffraction pattern, the superstructure peaks, and you see the disappearance of these superstructure peaks on charge, and they never truly reappear on discharge. So it's an irreversible process. And here's some lithium-6 NMR of the pristine material, and after one cycle. And the key point here is the center of gravity of these lithium signals. These are the spinning sidebands with the stars, has changed on discharge. So you remove the lithium ions, you put them back in again to the structure, but the lithium environment is different at the end of discharge compared with at the before charge. So this all speaks to this irreversible change on charging. So the message here is the honeycomb ordering is lost. There is largely in-plane transition metal disorder, and the lithium ions return to the layers, return to the transition metal layers, but in different sites from the sites that they were in before. Remember, you have lithium in the alkali layers and in the transition metal layers, and you remove both of those lithiums when you charge up to these across the oxygen redox plateau. So with all of that evidence together, we see molecular oxygen, we see disordering, we see an irreversible structural change. What do we think is happening to explain all of this? So here's our plan view of our pristine material here with the nice honeycomb structure. The lithiums are in the octahedra in blue here, oxygen's in red, of course, and we've just represented all the transition metal ions in one color to make it simpler in purple. So here's the material, the structure of the pristine material. Now we have at the end of the normal transition metal redox region, and of course we've removed lithium ions and oxidized transition metal ions. Then we will progress across the plateau. Now we have removed more lithium, all the lithium is gone, or almost all the lithium is gone, and we've oxidized oxide ions, shown by these sort of flashing images on the oxide. Of course, when we oxidize oxide ions, we're removing charge from the bonding states, and we're weakening the metal-oxygen bond. And as we do so, we can relatively easily, and I'll show you the DFT to support this, undergo this transition. So we've, if I go back for a moment, we get to this point, we've oxidized a number of these oxygens, we've weakened the metal-oxygen bonds, and we simply have to move 2 manganese ions, 1 hop in each case, to create this 4-vacancy cluster. And these 2 oxygens that you see here can dimerize like this to form molecular oxygen species. And of course, the driving force for this is that these covalent bonding interactions are lower the energy of the system quite significantly. So you can create clusters of this type. I'm not saying this is the only one. This is just one possible model cluster that shows you what is possible. And I'll show you in a moment the DFT to support this as being an energetically favorable process. And then when you discharge and put lithium ions back into the transition metal layers, you do not reform the honeycomb structure. I showed you this before. There's no recovery of this honeycomb structure. What happens is you reintroduce the lithium ions, but into different sites now, filling these cluster vacancies and reducing the molecular oxygen back to oxide ions. So if you contrast the pristine and end of discharge structures, you can see that they're different, and it's reasonable that the energetics of these 2 structures would also be different. Now, just to show you some DFT work looking at the energetics of some of these processes, what you see is the energy of different configurations here. And here the red cross represents the energy of our honeycomb, our sort of ground state, if you like, or our pristine material, and here are the vacancies. And so these gray crosses represent exploring different configurations, if you will, for the various vacancies that you see here. And of course, you get a range of energies as you arrange these vacancies in different sort of disordered configurations. But what you see here is that if you create a small vacancy cluster, even one with just 3 vacancies, allowing the formation of molecular oxygen, you reduce the energy of the system really quite considerably. And this is mainly driven by that covalent bond formation. And then this shows you that if you just have 1 more vacancy, you now have 2 molecular oxygens. And of course, this pushes the energy down even further. So you get a big step here and a slightly smaller step here. But the point is that by allowing these small vacancy clusters to form, you can accommodate the molecular oxygen in the structure, and it is a thermodynamically attractive process to do so. Of course, you have to move metal ions to do it and create these kind of environments, and that's the other part of this, which I'll mention in a few moments. But the message here is that you can weaken metal oxygen bonds, form the molecular oxygen that we see evidence in RICS, and I should say we've also carried out oxygen 17 NMR, which identifies also molecular oxygen in the structure and indeed allows its quantification, and that matches well with the charge capacity on this plateau. It's interesting, of course, if one thinks about this, there are two stable forms of oxygen, in the world mainly. There are oxide ions, and oxides, of course, are ubiquitous everywhere as stable solids. And there's molecular oxygen. Now, of course, there are other species like peroxides and things, but those two represent perhaps the most common and most stable forms of oxygen. And it's maybe not too surprising in hindsight why you would go from an oxide ion to oxygen. It's a different situation with sulfides. So to get a sense of what is largely contributing to the voltage loss on that cycle when you move from the nice plateau at high voltage to the curved discharge at much lower voltage, to get a sense of if you like, in terms of the electronic structure of what is giving rise to that big loss of energy, we can look at this. It's of course captured in the DFT, but just to get a sort of chemist's view, if you like, of the main elements of that energy change at an electronic structure level. I think this is a useful picture. So what we're going to focus on is the oxygen 2p levels, because those are the things which we're oxidizing, we're removing electrons from, and we're putting them back into. So this is the coordination around an oxygen in our pristine lithium transition metal oxide. The oxygen sits here between the alkali metal layers represented by the lithiums here, and the transition metal layers represented here. And as I said, in a stoichiometric material that doesn't have oxygen redox, all three would be metal ions, transition metal ions. The difference in a lithium-rich or oxygen redox material is you now have lithium in the transition metal as well as the alkali metal layers. And if we focus on this dumbbell arrangement here, this means that the oxygen 2p state here has only very weak ionic interactions. It's very weak covalent interactions, in other words, that it's only got principally ionic interactions with oxygen. And what this basically means is that these oxygen 2p states associated with this configuration will tend to sit at the top of the oxygen valence band represented by this red region here. So one finds in DFT that the nature of the highest energy filled oxygen states tend to have a lot of character from these interactions here. Now, when one looks at the same environment at the end of discharge, now we have oxide ions, where all of the surroundings are lithium. Remember, the lithiums go back into different sites, so the manganese is disordered, and these oxygens here are the oxygens that are now surrounded by lithium, not only in the alkali metal layers, but also now in what is a region of the transition metal layer. So now you have an oxygen you could regard as almost orphaned because it's just got very weak interactions in terms of overlap of the oxygen states with the oxygen 2p states with the lithium states. And overall, this pushes the oxygen states up further in energy. And this higher energy corresponds to a lower voltage. And this is, in essence, what is driving that loss of voltage and loss of energy that we see in the load curve. Now, of course, I mentioned that you can, after the first cycle, you can continue to cycle. And in this case, what happens, you oxidize the oxide ions again, you reform molecular oxygen, you come back down again, and the lithium ions go back into the same cluster. So this doesn't have an irreversible structural change. You still have some sort of breathing or distortions of the lattice, and that's probably responsible for the hysteresis, a slightly different pathway on charge and discharge, but much more structural similarity now, which is in keeping with the fact that we go around this hysteresis loop back to the same origin in contrast to the first cycle. So this is useful because it helps us to understand oxygen redox, but the question is, can we stop this happening? We would really prefer to carry out true oxygen redox by creating holes on oxide ions without molecular oxygen. So to get a sense of whether this is possible and how it might be possible, we looked at these interesting model compounds. So now we're moving to sodium intercalation compounds, but the principle is the same, with lithium on the transition metal sites only. And this is useful because we can use lithium NMR to probe what is happening only in the transition metal sites. So it's a rather nice model system. So what you're seeing here are two compounds, so-called P2 structure. That's because when you have sodium in the alkali metal layers, it prefers trigonal prismatic coordination. So this is the layered structure we have now. We still have transition metal ions, of course, in octahedral sites, but we now have sodiums, the larger sodiums in these trigonal prismatic sites. But the point here is these two compounds have the same crystal structure, very similar composition. Here we have 0.25 lithiums on the transition metal site. Here we have only 0.2. So very similar compositions, same crystal structure, really very different electrochemistry. One shows voltage hysteresis, the so-called 0.25 compound, and one, for a large part of its electrochemical curve on the first cycle, doesn't. This is what we would really like to have in our compound, coming back along more or less the same pathway on discharge as charge. So understanding these compounds will be helpful in thinking about mitigation of molecular oxygen formation. 0.25 compound, this is a powder diffraction pattern for it. It has the characteristic feature, you see it here, of the honeycomb superstructure, and it's represented here. Here's a bit of a clue to what's happening, because in the case of the 0.2 compound, small composition change, it has a different superstructure, one that we call a ribbon superstructure. You contrast these two. This is the honeycomb around the lithium. Here you see these ribbons, yes, represented by the purple shading. So it's a different arrangement of ions in the transition metal sites, a different superstructure. And this superstructure is to a large extent at the heart of suppressing the molecular oxygen. So if you look at the 0.25 compound, I'll go through this one quite quickly because it's got the same features we saw in the lithium compounds. Here's the pristine material, the dumbbells. You get the same disordering on charge. You're losing the honeycomb arrangement. There is an extra complication here that you go from a P2 to a O2 stacking, but the point is it's never recovered again. It's the irreversible process that you saw. In the case of this slightly different composition with the ribbon structure, you see a different arrangement here of these sort of four, not a dumbbell now, but these four dot features which are associated with the ribbon structure. It remains, this ribbon structure remains on charge and on discharge. And here's the powder diffraction pattern. Here's the pristine material on charge. These peaks appear to disappear, but they reappear on discharge. So it isn't that the structure is completely, if you like, immobile, but it's reversible. The structural changes that happen are much smaller, and they're reversible. They are reversible structural changes. You come back to the same arrangement on discharge, as indeed you have to, of course, if the voltage curve does the same thing. I'm going to skip one or two of these in interest of time, but this is some lithium-6 NMR, and I just draw your attention to this feature on the right. This is the ribbon structure. Here is the resonance for the lithium in the transition metal layer. Here is the lithium in the alkali metal layer. So when you take sodium out of this compound, the lithium in the transition metal layer drops into the alkali metal layer. Then when you put the sodium back in, the lithium pops back again into the transition metal layer in the same position. So there's reversibility here, whereas over here you can see the purple is rather different, representing the lithium now in a different environment. And if you carry out DFT on this system, of course, which unsurprisingly, because it has the same structure, you simply remove lithium, you retain the ribbon structure, you discharge again, you put the lithiums back into the same sites. Naturally, you come along the same, pretty much the same voltage curve, and the DFT predicts a voltage in this region for these structural changes. So the point is, you see that the ribbon structure, changing the superstructure of the transition metal layers, the ordering in the transition metal layers, doesn't allow the vacancy clusters to form that you need to permit the dioxygen to form that you would like to thermodynamically, but it doesn't allow this to happen. And this suppresses the so-called voltage hysteresis. Not perfectly, and indeed on cycling you do lose this. So this is not a silver bullet for the industry to have a material, but it, I think, scientifically shows us that it is possible to suppress the molecular oxygen and get true reversible oxygen redox. What is it about this ribbon structure that allows this to happen when it doesn't happen in the honeycomb? Well, here's a representation of the transition metal layers for three compounds. The compound we've been talking about a moment ago, the 0.25 honeycomb one that you see here, the ribbon structure that you see here, and another compound, the sodium 2 manganese 307, which I call a mesh structure. And you see they have different arrangements of the lithium vacancies. So these are the transition metal ions in purple, and we've charged the cathode, removed lithium from these lithium sites in all cases. Now, as I showed you before, just 2 manganese displacements create the conditions for molecular oxygen to form here. In the case of the ribbon structure, you have to undergo rather more displacements of manganese before you can create a vacancy cluster that would allow or permit the formation of molecular oxygen. And of course, in the mesh structure, you could see even more separation of lithium vacancies will become even more difficult for them to come together, requiring multiple manganese displacements. And this is in large measure the reason why you get suppression of the of molecular oxygen formation in the case of these other superstructures. So the superstructure on the transition metal layers can help to suppress molecular oxygen formation and trapping in the bulk. I won't dwell on this slide. It just shows you that, as I say, this material will disorder on multiple cycling. I think the interesting point on this slide that I wanted to bring out, these are some X-ray absorption spectra as opposed to RICS. And on the left, you see the pristine spectrum in black, the charged spectrum in red, and the discharged in blue. And this is for our honeycomb structure again. And so these extra absorptions here represent, now we're mapping out the whole states above the Fermi level. This represents the molecular oxygen formation. In the case of the ribbon structure, you see a new feature here at about 528 eV. And this is the first real, I think, evidence of true oxygen redox. These are whole states on oxide ions, which are reversible. There's a small amount of molecular oxygen as well, as I mentioned, but this is the feature that I think is another signature for this changed behavior. And I think I should draw this to an end really with this slide here. Because what this means is that we can have a single unified model for oxygen redox. That when you oxidize oxide ions, unless you have suppression mechanisms that I've just shown, you will favor the formation of molecular oxygen wherever this is possible. And at the surface, of course, it's relatively easy and you can just evolve oxygen. It's more difficult in the bulk because it requires some metal ions to move to accommodate them. But we have a single unified picture now of molecular oxygen being the destination of oxygen redox. So here's a representation of a lithium-rich so-called NMC, and this represents the surface and the bulk. And we're going from the top to the bottom here, to this region. We're oxidizing the oxide ions. So at the surface, what happens is you lose molecular oxygen, you get metals migrating into the vacant lithium sites, and you get this so-called densification process. The key thing here is, as you do this, you move the composition of this near surface region close to a stoichiometric composition. It's no longer lithium-rich, no longer oxygen redox active. And so this self-limits because of that, because once you've got a stoichiometric composition, then you've nothing to drive further oxygen loss and metal migration. In the bulk, so this stops, and the only other thing that can happen, the only game in town for the oxygen, molecular oxygen, is to get trapped in these vacancy clusters that I represented here. So I think my time is up, so I'm going to skip the next few slides and just go to the acknowledgements. I was going to tell you a little bit about how the substitution of various transition metals can have a huge effect on how much oxygen loss at the surface one encounters, and that's one of the reasons why the nickel-doped lithium manganese oxides have such low oxygen loss when Li2NO3 is 100% oxygen loss. But in view of time, I won't go through that. I simply want to end by saying that I hope that you can see that the work that we and other excellent groups around the world have been doing on this, I think, difficult problem for the last few years, I think has helped to make some significant progress in understanding a problem that's been with us for 20 years, that it appears that molecular oxygen has an important role to play, which takes us back to the work of people like Jeff Dunn and Mike Thackeray when they worked on these materials initially and thought everything was about oxygen. It may well be the case. It's just that some of that, a lot of that oxygen is actually trapped in the bulk. I want to thank my co-workers that you see here who have done the work, the various funding agencies that have supported us, and of course, most of all, to thank you all very much for your kind and patient attention.
Thank you very much. I think it is really obvious to see how here chemical models and chemical pictures merge with physical pictures of band structures, the typical chemical picture of orbitals, the physical picture and model of bands of a band structure really are combined to understand complex phenomena. And I think what I also like is the fact that what is typically a paradigm in solid state chemistry, that cations that do the story and do the job are simply dissolved in an anion solvent, where the solvent is not doing anything. So here, I think it's nice to see that the anion solvent also is contributing and can be quite active. So I think we have room for some questions, and I ask the virtual audience and of course the audience here in the room. I probably then recall the questions so that everybody can understand. So do we have questions to Peter? Whatever it is, as specific or as general with respect to battery materials. Peter?
The discussion was on a microscopic level, but of course other length scales also play a role. How much in case of the voltage loss during the first cycle?
Okay, so Peter from physics here asked that you discussed now the process very much on the atomic level. And there is, of course, there may be consequences on other, let's say, size levels. I also thought of, let's say, maybe there will be volume changes. And we know that for cathode materials, there is this cracking may occur due to volume changes. So what happens on other length scales if these oxygen defects fall?
Yes, I'm having a little bit of difficulty hearing you in the hall, but I think if I've misunderstood the question, correct me. But I think it's a question of length scales. I mean, I think the first
different length scales. Yes.
Yes. So I mean, the first thing to say, of course, is that the balance. I didn't get onto this bit of the talk as you saw at the last few slides, but of course, the balance of how much oxygen loss from the material, that is, oxygen lost from the surface, versus how much oxygen is trapped in the bulk, is a function of to some part of the particle size. So if you have very, very small particles, if you go to the real nanoscale, of course you increase the amount of oxygen loss compared with the amount of oxygen redox. So that's perhaps at the very simplest level a very significant influence of length scales on what happens. I think it's a very good question, the extent to which this structural disruption that we talked about on the atomic scale will have impact on the mechanical properties of the particles. The extent to which this will cause cracking or fracturing of the particles, I think, is an absolutely important issue. It is not something that we have done very much on, so I don't want to really commit any view to it right now. But I agree with the point, and I agree that it is an important potential issue. I would also say that, interestingly, in practical terms, as I think I touched on, there are two ways one can exploit these materials. One could hopefully suppress the molecular oxygen and really use the high voltage. But of course, a lot of people are trying to use these materials accepting that you lose the first cycle energy and just work on subsequent cycles. The difficulty is that to do that, you have to modify the surface and produce core shell structures or coatings. And there's quite a lot of evidence that it's very challenging, shall we say, to have these core shell structures, especially with these lithium-rich materials, and avoid cracking and fracturing and losses there. So people do this with stoichiometric materials, especially graded compositions, with some success. It's another step up in challenge to do it with these lithium-rich materials.
Okay, thank you. Do we have more questions here from the audience here? Doreen, I tried to repeat this question from theory. So Doreen is our theoretical chemist, and Peter, she asks what type of level of DFT was being used for the theoretical calculations, and Doreen is suspicious of it because she says that particularly oxygen seems to be difficult with some of the DFT calculations. I'm not a specialist, but I hope that I repeated the question correctly. Yeah.
Well, I can only say that you're having to translate this between two non-specialists in this area, because I join you in this one, Jürgen. This is very much the collaboration with another colleague. So I can only give you probably a partial answer to your question. I mean, two things I'll say. He and I, but more importantly, he does recognize the challenges of modeling oxygen, and so I think he's very aware of that, and I believe he has taken care of it. It is based on hybrid functionals, but beyond that, I really don't know that I can help you answer this question. Answer the question. I'm very happy if you wanted to email me to give you more details. It's not that I'm avoiding it. It's just that my level of depth of knowledge here is probably not enough to give you a good answer to your question.
Okay, very good. I think Doreen is very interested in the oxygen, quantum chemistry of oxygen. She'll mail you. I got a few questions via phone, and one of the questions simply is, if really a substantial amount of these, let's say, oxygen molecules form in the lattice, shouldn't that be seen by some variation of vibrational spectroscopy, either Raman or infrared spectroscopy, depending really on the species?
Yeah, I mean, we've looked at several different techniques to try to do this. I mean, one might imagine that the very best one would actually be EPR, and of course, some other people have used EPR in this field before. But I think the short answer to the EPR question is that it is very, very difficult to really extract reliable, convincing evidence from EPR in these sorts of systems. It seems very appealing. You would think molecular oxygen would be the perfect thing to detect with EPR, but it turns out not to be the case. I did touch on, I think, very briefly the fact that we haven't shown any data here, but we have used oxygen 17 NMR, which is also a difficult technique, but we have had success with that. And so that also detects the molecular oxygen. The problem with Raman is, of course, that Raman tends to be a little bit selective towards the near surface regions. And one of the concerns we had about all of this, why again we like RICS, is that a lot of techniques like Raman, and especially, of course, X-ray absorption as well, it's a different technique, but I just also talk about on XPS, are techniques that tend to be rather surface or near surface dominated. And why we find NMR useful is because it's a true bulk average technique, and even RICS because it's it's not an absorption technique per se. It has a depth of around 50 to 100 nanometers, so you can be more confident that you're really probing well below the surface. Because one of the things that concerned us is whether we could be picking up, oxygen absorbed on near surface or surface regions or something like this. So those are the reasons behind the two techniques that we've used. We have looked at Raman. Others have used Raman. Honestly, we're not convinced that Raman is really able to probe the processes, the nature of these species in a convincing way. And whether we've looked at materials where people have claimed Raman signatures with other techniques, we haven't found them.
Okay, thank you. Yeah, so we have a question from Max, who's in physics, physicist moving into physical chemistry and material science, and his question is on the advanced structure picture, where the oxygen story, of course, is discussed being in terms of the oxygen S electrons, and he asked what happens during these extreme, let's say, processes with the oxygen to the D states.
So maybe let me just clarify, because the oxygen processes that I was focusing on were in the P states. The only oxygen S state was in the RICS experiment, where what happens is the incident radiation excites an electron from the core shell, from the 1s state, up to the empty states above the Fermi level. And then you look at the electrons below the Fermi level dropping back into the core state, and that gives you the emission spectrum. So that was the sort of, this if you like, the technicalities of the measurement. But the oxygen states that I was focusing on, the ones that are carrying out the redox processes, are absolutely the 2p states. And it's the interactions of the 2p states with the lithium or the manganese states that is central to controlling the position of those oxygen 2p states that changes between the charge and discharge process that's at the heart of it. So apologies if that was confusing. But the 1s is only part of the technicalities of the RICS experiment, and it is all about the 2p.
Okay, so I have a question from our virtual audience, from Bernd Marcy, who is here, professor in inorganic and physical chemistry, and is an expert for nanostructured materials. So he asks, he says, in the first part, the XRD data show that the material in the charged state appears to be quite amorphous, at least XRD amorphous. And he asks whether this isn't really a problem for discussing what is going on in the material, because you seem to lose the long distance symmetry by amorphization. Is that the case?
I think you lose the long range ordering when you charge these materials. They always tend to see the peak broadening quite significantly. But in the case of the ribbon structured material, I think you saw that on the discharge you recover the peaks, and they look very similar to the pristine materials. So this is a reversible loss of the long range order, but is recovered on discharge. Of course, in the materials that lose the voltage, that exhibit the voltage hysteresis, there the loss of order is essentially complete and irreversible. I mean, he makes a very good point, and that's really part of the reason, or a large part of the reason, why we used STEM and NMR, because they are local probes, whereas with X-ray diffraction, of course, once you lose the long range, the nice long range order, you lose it's much more difficult to extract structural information. What I'm saying is there's nothing inconsistent in the X-rays that we saw. The materials that do not exhibit hysteresis show very nice reversibility in the diffraction patterns. The ones that show hysteresis do not. But I think the more insightful, if you like, techniques for understanding this are the local structural ones of STEM and NMR.
Thank you. Okay, maybe a final question from obviously a enthusiast in defect chemistry, Peter, is the question: if we form these oxygen species, it looked in your graphs as if one of the oxygen atoms still is more or less on a regular oxygen side, while another oxygen atom moved closer to that oxygen. So can that second oxygen atom that forms then, or that comes closer to form something which can be considered as an oxygen molecule, can be represented as a kind of interstitial oxygen ion, or how would one, well, I'm not sure whether one needs to describe that in terms of, let's say, defect chemistry and kind of Krüger-Fink notation, whether that makes sense, but is that then the second atom that moves to the other atom something like an interstitial oxygen ion?
No, it's a very good question. I mean, the trouble with cartoons to try to show overall pictures of processes is that they can be, the danger is of overinterpretation. That's no criticism of the questioner. I absolutely agree with them. I don't think you should take too literally the precision, if you like, that's in the cartoon. In fact, the evidence is that the vibrational spectrum of molecular oxygen observed in this material is very similar to molecular oxygen in the gas phase, which implies that the interactions with the surrounding manganese or whatever at most is relatively weak interaction. It's more of a sort of trapping than a bonding process from what we understand so far.
Okay. Thank you, Peter. I think all curiosity has been satisfied. And I think we thank you very much again for giving us your time and for this fascinating insight into what's a fascinating subject, unusual considerations of, let's say, the anion solvent in oxides. And I'm pretty sure that that work will continue and trigger further work. It has lots of, I would say, implications to other subjects in solid state chemistry. And with that, again, my thanks, and of course the thanks of the two audiences in the virtual reality and present here to excite us for our event today. Thank you again, and I think also the audiences in the virtual world and here for joining, and I close the seminar. Thank you.
Thank you very much, and apologies it's so late.
Thank you, Peter.
Thank you very much. And as I say, apologies it's so late and the confusion over time, but I appreciate
everything. No, everything is fine. I think we were confused ourselves. Okay, bye, Peter.
Stay safe, everyone. Thank you.